Okay. Uh, we um, I already explained that how many methods do we have uh, to improve the quality of the insulator, and this slide present the concept of conducting glasses as an alternative method for improving voltage distribution in insulator strings. Did you remember I told you that voltages is better to be uniformly distributed across all of insulators in the strings. So the idea is that to apply a semi-conducting glass on the surface of the insulators, which introduces a control leakage resistance along the string. And this resistance effectively shunts the self-capacitance of each unit, and it can reduce the impact of them. Let me add a new student. All right. When the leakage current through this resistance pass, and this leakage current is sufficiently large, it dominates over the capacitor current. As a result, the voltage distributions will be more dependent on the resistance rather than the capacitance, and it can lead to a more uniform division of the voltage across the insulator units. So another point is that although this method is mainly of informational interest and not as widely used as other methods, it's demonstrating that an important principle of controlling electric field distribution through the resistive means, and it will use this principle to reduce the impact of the shunt capacitance in insulators. Okay, this slide explain more the practical implementation and limitation of the conducting glass method. The approach involves coating the surface of insulators with a semi-conducting glass, which effectively provides a high resistive pass in parallel with the self capacitance of each insulator unit, and this will add some more resistance, allows leakage currents to follow, and helping to equalize the or uniform the voltage distribution across the string by reducing the dominance of capacitive effects. However, a major challenges here is that this method is maintaining the long-term stability of the conducting glass, and over time also we will have environmental factors such as weather, pollution, and aging can degrade its conductive properties, and it will make it less effective to reduce the shunt capacitance. So due to this reliability issue, the method is not widely adopted in practice in comparison to other methods. Okay, this slide highlights key points about the voltage distribution along a string of insulator disc. It is important to note that the maximum voltage appears across the disc closest to the line conductor and making it the most electrically stressed component. Additionally, the total voltage across the entire string is equal to the phase voltage, which is defined as the voltage between the line and earth. And finally, the relationship between the line voltage and the voltage across the strings also is given by the equation you can see in this slide, uh, where the line voltage equal square 3 times the string voltage. And these concepts are very essential for understanding insulation design and also ensuring that the reliable performance in HV transmission system will be completing it. Okay, this is an example. Consider 33 kilovolt overhead transmission line equipped with a string of three insulator units. It introduces the effect of capacitance between each insulator pin and earth, which is given as 11% of the self-capacitance of each unit. The problem focuses on determining how the total voltage is distributed across the three insulators, highlighting the non-uniform nature of the voltage sharing due to these capacitance effects. In addition, it requires the calculation of string efficiency as an important parameter that indicates how effectively the insulator string utilize its units under operating conditions. And this example helps in understanding practical voltage distribution and performance evaluation in high voltage or HV insulation systems. As I told you, the distributing voltage across the insulator in the strings is a key point. So in this slide, I present the detailed solution for determining the voltage distribution across the three unit insulator string in 33 kilowatt overhead line. We already discussed about this figure. The analysis begins by modeling the system using an equivalent circuit that includes both self-capacitance of each insulator and shunt capacitance, where K is given as 0.11 and the total voltage across the string is first calculated from the line voltage, yielding a phase voltage of 19.05 kilovolt. By using of Kirchhoff current law, KCL, at different junctions, the current and voltages across each insulator disk can be expressed in terms of top unit voltages, V, and at junction A, we already discussed about this equation. And junctions A, the relation between the first and second unit voltages is established, showing that the second unit experiences higher voltage due to the shunt capacitance effect. Similarly, applying the same principle at junction B, provide a voltage across the third unit, this one, and which turns out to be the highest among all three insulator. I already told you this one has a maximum voltage. So this step by step, the derivation uh, clearly demonstrate that the voltage distribution is non-uniform. You can see that. For example, V is equal to 19.05 kilovolt, but V2 is 1.11, V3 is 1.342 V1. And um, and this formulation also set the foundation for calculation string efficiency, emphasizing the importance of proper insulation design in HV systems. So next, uh, we can continue to calculate the rest of the equations. You can see V is equal to V1. This is a KVL. V2 plus V2 plus V3. So we already calculated all of these variables. So we just need to replace the values. And also, in my last lecture, I told you what is the relationship of string efficiency. So voltage across the strings divided by number of insulators times the maximum voltage V3. So uh, it this slide showing that the total voltage across the string can be expressed as a sum of voltages across individual units, and where unequal voltages can be summed together, and also this non-uniform distribution reduce the overall efficiency of the string. The string efficiency is uh, calculated as 85.8%, indicating that the insulator units are not equally utilized, and bottom unit is subject to the highest the electrical subject stress, and there is more probability to get to be failed in the future. So this is another example. Consider a three-phase transmission line supported by a string of three disc insulators. The voltage across the top unit nearest the tower and the middle unit are given as 8 kilovolt and 11 kilovolt respectively, indicating a non-uniform voltage distribution exists along the string. And based on these values, the problem involved determining the ratio of capacitance between the pin and earth relative to the self-capacitance of each unit. Furthermore, the total line voltage and the string efficiency can be calculated, and this analysis can help us to highlight the impact of capacitance on voltage distribution, and will demonstrate how unequal voltage sharing affects the performance and efficiency of insulator string in high voltage transmission system. Okay, this is in this slide we want to analyze the voltage distribution across a string of insulators using an equivalent capacitive circuit model. Each insulator unit is has been represented by its self capacitance C, while the capacitance between the metal fittings and earth is modeled as Kc. We already talked about the Kc, so in previous one, K is a fraction part of the series capacitors. So we have a Kc, and K is a ratio of shunt capacitance to a self capacitance, and the given voltages across the first two units are V1 is equal to 8 kilovolt and V2 is 11 kilovolt according to the question. To determine the unknown parameters and total voltage, we can apply KCL at the different junctions. So at junction A, we already discussed about this equation. This is a simple KCL. So V2 is equal to V1 times 1 plus K. So we can find the K, very simple. And next, we can apply the KCL for at junction B, and we can obtain another current balance equation that indicates the uh, cumulative effect of voltages across multiple units. And this leads to the expression of Vc is equal to V2 and V2 plus V1 plus V2 times K, because WC can be removed from two sides. So substituting the known values, we can find the V3 is equal to 18.12 kilovolt. Summing the voltages across all three units gives the total phase voltage to earth, and V is equal to V1 plus V2 plus V3. So Finally, we will have this value for V, and this is a three-phase system, so the line voltage will be equal to 64.28 kilovolts. So this example clearly is illustrating how a non-uniform voltage distribution across long and insulator strings due to the presence of shunt capacitance is working, and the unit closest to the line conductor typically experiences the highest voltage stress, which is a critical consideration in high voltage transmission line design and very important. Okay, uh, in this final step, we we have to evaluate the string efficiency, which is a key performance indicator I told you before. So we can use this equation, and string efficiency is 68.28%. So this result is showing that the voltage distribution along the insulator string is not uniform, and ideally if the voltage were equally shared among all units, as I told you, the efficiency should be 100%. However, due to the presence of shunt capacitors represented by K, the unit closer to the conductor will have the higher voltage stress, and leading to the reduced efficiency. So uh, this is a very low efficiency. In practical application, techniques such as using grading rings or optimizing the insulator design can be employed to improve the voltage distribution and increase of the string efficiency. Okay, this is another example. We want to analyze the performance of a string of insulators used in a three-phase transmission line. Each phase conductor is supported by a string of three identical insulator units, and it is given that the voltage across the line and insulator, the unit closer to the conductor, is equal to 17.5 kilovolt, and additionally the shunt capacitance between each insulator and earth is assumed to be 1/8 1/8 of the self capacitance of each unit, which means that K is equal to 1/8. So the objective of this problem is two reasons. First, to determine the total line to natural voltage across the insulator string, and second, to calculate the string efficiency. So we already discussed completely about this figure, so we can apply the KCL for this junction and this junction, and we can find simply the V1, V2, and V3 for each of across each capacitor capacitance, series capacitance. So we can have V at the end. V is equal to V1 plus V2 plus V3, and string efficiency also can be used, can be calculated based on this equation. So we will have 84.28%. So this result is highlighting that due to non-uniform voltage, again, the string does not utilize all units equally, and the string efficiency has been reduced. Okay, this slide presents another practical example related to voltage distribution in post-type insulators used in an outdoor substation. In this case, three bus bar conductors are supported by insulator units, where each unit is made up of the stack of three pin-type insulators placed on one uh, one by one each other. So the given datum specify that the voltage across the lowest insulator is equal to 13.1 kilovolt, and the voltage across the maximum voltage in across the nearest capacitors to the conductor is uh, and the minimum, sorry, the minimum voltage across the closer capacitor closer to the top is equal to 11 kV. So using this information, the objective is to determine the total bus bar voltage of station. And this example also highlights how voltage is unevenly distributed across insulator units and demonstrate the method of calculating the overall system voltage based on individual unit voltages. So again, we need to um, make KCL in two junction and find the V1, V2, and V3. So uh, we don't, and finally we are looking for K. So just we can replace the um, all values in two KCLs, and we can find this second order equation. So um, this is providing the solution, and this equation can be solved to find the value of the K, and this process highlights how circuit analysis techniques can be effectively used to quantify the impact of shunt capacitor on voltage distribution in insulator strings. Okay, and uh, this is V1 is equal to V2 divided by 1 plus K. So solving this equation, we can find that we will have two values for K. One of them is a negative value, so we can ignore it. And this is a second value. So K is equal to 0.1, so we can find V1, and then uh, we have V2 and V3, so the total voltage can be calculated easily, and the uh, line voltage also in three-phase system is equal to, can be calculated based on this. And this result is showing that in a line voltage of approximately 59 kilovolt, and um, this slide effectively can conclude the example by linking the detailed voltage distribution analysis to the overall system voltage and reinforcing the practical importance of this calculation in high voltage in HV systems. All right, this is another example. So this example focus on three unit insulator string again, where each unit has a safe working voltage of 15 kilovolt, and the ratio of self capacitance to shunt capacitance is given as 8 to 1. So the objective is to determine the maximum safe working voltage of the entire string as well as the string efficiency. And this type of problem is, as I told you, is very important in HV systems because it evaluates how effectively the insulator string utilize its individual units under non-uniform voltage distribution conditions. So in the solution, the ratio of K is first determined as 0. So 1 over 8 is equal to 0.125. Since the maximum voltage appears across the unit nearest to the conductor, the lowest unit is uh, assigned the maximum um, allowable voltage of 15 kilovolt. By using FKCL at junction A, we will have this equation. I just want to skip again to explain all of this. So By using of these two KCL in junction A and B, we can find the V1, V2, and finally V. String efficiency also can be easily calculated. So this is also another example. Uh, this example focus on voltage distribution across a string of 4 suspension insulator. Here, instead of 3, we will have 4 insulator. Specifically, it examines how the presence of shunt capacitance, pin to earth capacitance, affects the voltage sharing among the insulator units, and it also aims to determine the string efficiency. The, the key point of the problem is that each insulator has a self-capacitance that is 10 times the shunt capacitance, meaning that the K is equal to uh, 10, C divided by C1. So this non-uniform um, capacitance cases the voltage. uh, it will make some voltage distribution along the string to become um, ununiform, and which is an important consideration in HV transmission systems, as I told you. And to solve the problem, then nodal equation method is can be simply applied. Did you remember nodal equations from the power system 2, right? So by using of reactance for the self-capacitance, so XSC is equal to 1 ohm, since only the ratio of capacitance affect the results. And based on the given ratio, the shunt capacitive reactance becomes XC1 um, is equal to 10 ohm. So the solution proceed by assuming a current of 1 amp following through the top insulator. So using circuit analysis, you can the current through each insulator can be calculated by accounting for the additional current flow following through the shunt capacitance at each node. So as a result, the current increase progressively from the top unit to the bottom unit, and by multiplying the current through each insulator by its reactance 1 ohm, the voltage across each unit also can be calculated. So these voltages are found to be unequal, as you can see, and the voltage across each unit is will be unequal. And finally, the total voltage across the whole string is equal to 5.06 volt. Okay, this is a single line diagram of insulators. We have 4 insulator connected in series and 3 shunt. And here you can see the values of voltages and the current are passing through each transform capacitors. Okay, this slide complete the analysis by expressing the voltage across each insulator unit as a percentage of total string voltage, and then calculating the string efficiency. So after determining the total voltage across the string is equal to 5.06 volt, the voltage contribution of each unit is can be normalized with respect to this total value. So the percentage voltage across the each unit can be calculated by dividing the voltage of each unit by the total voltage and multiplying by 100. So we can use this value. So and finally we have a total voltage and the maximum voltage. So we can, and the number of string is equal to 4. So string efficiency will be equal to 76.6%. So this result indicate that string is not fully efficient as the voltage is ununiformly distributed and the lower units are subject to the higher electrical stress. Okay, this is another example, uh, um, and this is slide present example 8.10, which applies the theoretical concept of voltage distribution in a suspension insulator string to a practical case. In this example, each insulator unit has a self-capacitance C, while the shunt capacitance between the metal fittings and earth is given as 0.15 um, capacitors, and the capacitance between each unit and the line is equal to 0.1. See, the slide first illustrate the physical arrangement of the insulator string and then its equivalent electrical circuit where the different capacitances are can be clearly represented. It is also showing that the line capacitance is relatively small, and and um, um, it can be often um, ignored to simplify the analysis. Using this equivalent circuit, the problem aims to determine the voltage across each insulator as a percentage of the total line voltage, as well as to evaluate the string efficiency. This example help us to make a bridge between the theory and practical by showing how capacitance affects influence voltage distribution and how you can analyze and design insulator strings for one HV transmission system. So let's move on to solution. Again, we can apply some KCL in these two junction. So this is a solution. So we can apply KCL at different junction of the equivalent circuit. At junction A, the sum of KCL is equal to the sum of incoming and outgoing current should be equal. And we can write this one, and then I2 we can replace voltage instead of current, and this equation is then simplified to express V3 in terms of V1 and V2, as you can see in this equation. And similarly, at junction B, KCL will be applied again to form another equation involving the same voltages by substituting the expression for V3. Uh, V3 obtained from the first equation, from this equation, into the to this equation. We have two equation with three variables, so one of variable can be removed. So solving this equation, we will have finally we can have that V2 is equal to this equation. So we can apply a step-by-step approach, and we can analyze the circuit to determine the non-uniform voltage distribution across the insulator stream. So this slide complete the numerical solution of the previous example by determining the actual voltage distribution across each insulator unit. First, the previously um, um, expression for V2 can be substituted into the um, equation to calculate V3 in terms of V1. So we can just substitute V2 in terms of V1 in here. So, and finally, V is equal to, can be expressed by this equation only based on the V1. So, and V2 is equal to this one. We can find V1 and V2 and V3 respectively. So this result clearly confirmed the non-uniform voltage distribution with the disk nearest to the conductor. And the final step is showing the effect of capacitance on voltage sharing in insulator string. So this is a final step. Top unit, we can find all of voltages. So, and then we can calculate the string efficiency based on this equation. So we will have our string efficiency is 91.5, closer uh, to 100%. So is the the efficiency has been improved a little. So this is another example which focus on improving the voltage distribution and string efficiency again. Similar to the previous one, but we install a guard ring here. So as I told you, when we install a guard ring in combination with our insulator, we will have the capacitors, and these capacitors can reduce the impact of the shunt capacitors. So we need to again write the KCL for at each junction, junction A and B, and replace the current with a voltage. So uh, V3 from this equation can be based on this. In terms of V1 and V2 can be calculated based on this equation. So in at junction B also we will have similar questions. So two equations, we have three variables. One of the variables can be removed, and we will have V2 in terms of V1. So we can put V2 in one of previous equations, and we will have V3 based on the V1. So V, the total voltage is equal to 3.0.7 V1. So, and V3 is the maximum value, so can be calculated based on this, and string efficiency, we can just put it here, and V1 can be removed from two sides, and we will have 95% efficiency. Okay. Uh, we are using this reference mainly for this lecture. Okay. Do you have any question? If not,